Today, atomic structure is something that we take for granted. That the atoms consist of a nucleus with protons and neutrons and electrons floating around the outside may seem like common sense to you. But that wasn't always the case. In fact, we really didn't fully understand what the atom looked like until the middle of the 20th century. Crazy! In this video, we'll hit the highlights of how we figured out what atoms looked like, along with the specifics of the experiments that were used, and some of the ideas that scientists came up with along the way about how the atom looks. The idea of the atom is actually very old and is attributed to Democritus, a Greek philosopher who first postulated atomic theory, or that the elements are made up of individual units called atoms that are unique to that element, around 400 BCE. I'm not so concerned about you knowing the specifics of the discovery so much as I care that you know that atomic theory had its roots in ancient Greece. Now, Democritus's theory held weight, as elements of his theory have been experimentally proven thousands of years later. But Democritus's theory was just that, a theory. It didn't yet have any experimental evidence to back up his claims. Ancient Greece and Rome were very developed, but not much happened in atomic theory for approximately 2,000 years. Why? The fall of Rome, the Dark Ages, etc., and the next major developments didn't happen until the 17th and 18th centuries. What major event precipitated this development? Well, the Enlightenment, of course. In Europe during this time, great thinkers such as René Descartes of Je pense donc je suis fame placed a great emphasis on rationality. You had several scientists and thinkers decide to use the rational framework laid out by philosophers to study the natural world or nature around them. So in the 16, 17, and early 1800s, we see a burst of knowledge about the atom come into being as scientists were building an experimental framework to study the world around them. In this outline, I've highlighted Antoine and Marie-Anne Lavoisier, who, along with several other scientists that are talked about in the book, laid the experimental framework that allowed us to learn about the atom later on, and also helped us to understand a lot about some of the early elements. Now, in terms of atomic theory, it came to a head in 1803 when an English school teacher named John Dalton built both on the work of earlier scientists as well as his own experimental work, laid the groundwork for atomic theory, which are listed here in the notes. I won't read them aloud, but with the exception of one special case, these laws have held up the test of time and have been proven by subsequent experiments. Now, the 19th century was a great time for scientific advancement, but in terms of atomic theory, the next big breakthrough doesn't really happen until the end of the century, almost 80 to 100 years later. Why did it take so long? Well, take a minute, put on your liberal arts thinking hat, and think about it for a quick minute. What major event happened during the middle and late 1800s that might have resulted in new technology for us to do science with? If you came up with the Industrial Revolution, you're correct. So from ancient Greece, the idea was there. After the Enlightenment, we gained a scientific method or framework to design, execute, and interpret experiments to get an idea about what an atom actually is. And then finally, after the Industrial Revolution, we made enough advances in technology that allowed us to make some real progress in understanding how the atom is composed. Specifically, what are the individual parts of the atom and how are those parts arranged? The next big experiment or discovery was performed by J.J. Thomson and his co-workers in 1897. J.J. and company used a cathode ray tube. If you're not familiar with what a cathode ray tube is, here's a picture of one. It's a long tube that has a power source that generates an electrical current that runs through the length of the tube. At the end of the tube, the current, which contains electrons, hits a phosphorescent screen. These cathode ray tubes, so one shown here, were the basis upon which old school televisions were built. What Thomson did is he took a cathode ray tube, a diagram shown in the center here, and he turned it on, which led to a beam of electrons. And so what he noticed is when he put a magnet around the cathode ray tube, the electrons, after flowing through and reaching the magnetic field, were deflected in a way onto the phosphorescent screen that would be consistent with how a negative charge would act in the presence of a magnetic field. Then, after Rutherford removed the magnet and instead applied an electric potential by putting positively and negatively charged plates on either side, he noticed that after applying the electron beam, it was deflected towards the positively charged plate, which again would suggest that the electric beam contained negatively charged particles. However, when Thomson applied both the potential and the magnetic field at the same time, the beam went in a straight line, or the effects were balanced out. From applying a magnetic field and charged plates, Thomson was able to determine that the charge-to-mass ratio was negative 1.7588 times 10 to the 8th coulombs per grams. After his experiment, Thomson came up with a model for the atom based on his observations. He knew that the electrons, although he didn't call them that, he called them corpuscles, were negatively charged. It was also known at the time that atoms were neutral, so there had to be some sort of positively charged component in the atom to balance out the charge of the corpuscular electrons. So Thomson proposed what was called the plum pudding model. If you're not familiar with plum pudding, which is an English dessert, here you go. You'll notice that plum pudding isn't pudding as Americans think of it, but rather a sticky cake-like substance with raisins or sultanas stuck in the middle and scattered throughout. Thomson proposed that the corpuscles or electrons were like raisins, while the positively charged component was like the cake. Another way that I like to think about it is those delicious Keebler M&M cookies that my grandma used to give me when I was a kid. The electrons would be the M&Ms, while the positively charged portion would be the cookie. Let's draw it out for our outline. These defined areas would be our negatively charged corpuscles, whereas the positively charged would be distributed across and around the negatively charged areas. So we have the charge to mass ratio now, and it's right here in legible writing for you, but we didn't know either the charge or the mass at this point. So the next step was to independently measure either the mass or the charge of an electron so we could figure out the other value. Fortunately, in 1908, Robert Millikan and his team stepped up to the plate with an oil drop experiment. Millikan set up this sweet little apparatus where he took some oil and vaporized it. Think of an old school perfume bottle or a spray paint can. The oil droplets were then sent into a container which contained a positively and a negatively charged plate. Now, the oil droplets themselves are neutral, so they would drift down into the container until they hit a laser, which is represented here by the wavy lines. Now, this laser would ionize the oil droplets or give them a negative charge, as an ion is something that contains a charge. Before the laser was applied, the oil droplets were only being pulled down by the force of gravity. But once they were ionized and contained a negative charge, the oil droplets would not only be pulled down by the force of gravity, they would also be attracted to the positive plates based on charge, which I'll represent here by Z, which abbreviates charged attractions. And what Millikan did was he varied the strength of the electric field, and the triangle here stands for change, which then varied the charge that would attract the oil droplet. And so by varying the strength of the electric field and taking into account gravity, Millikan was able to calculate the charge that the molecule would have to carry to remain suspended in space. Then, once Millikan had the charge of the electron, he could take Thompson's value and calculate the mass of the electron. I've included both of those electrons in the outline. Now, in case you're wondering how Millikan was able to figure out and watch that this was happening, he had a hole in the apparatus where he could watch the oil droplets fall. So after Thomson and Millikans experiments, our understanding of the atom was that they had negatively charged corpuscles, which we now knew the mass and charge of, and we knew that they were pretty small. We weren't so sure about the positive charge, other than it had to be equal in magnitude to the negative charge to make a neutral atom, and the best explanation that we had was Thomson's, that there was a cloud or cake of positive charge surrounding the electrons. Scientists like to provide evidence for theories. So after Thompson and Millikans experiments, other scientists were trying to design experiments that could either prove or contest Thompson's models. One of these scientists was Ernest Rutherford and his team. Rutherford et al. Used radioactive atoms, rich-release particles, to prove his point. Today we'll mention two types of particles. Alpha particles, which are essentially helium-2 plus ions, or 2 protons, and beta particles, which is when individual electrons are emitted. Rutherford took an alpha-emitting material and put it into a box that had a slit. He then lined up the slit with a page of gold foil, and behind the gold foil was a concave screen. The idea was that the alpha particles would pass through the gold foil because it was known that the atoms contain empty space, and the angle at which they hit the screen would tell us about the structure of the atom. What do I mean by that? Here we have Thompson's model of the atom, with the corpuscles and the amorphous positive charge. If we were to send positively charged alpha particles through the gold foil, so this Thompson atom being one gold atom in the gold foil, the alpha particles would pass through the atom since it's mostly positively charged space, except periodically an alpha particle would hit a corpuscle. Now, the corpuscles weren't very big, so the alpha particle would only be deflected very slightly. When Rutherford ran his experiment, if he wouldn't have used the curved screen, his data might have suggested that Thompson's model was correct. Remember here that the gold bar represents a gold foil, which consists of individual gold atoms. Most of the alpha particles that were emitted passed straight through. However, some alpha particles, approximately 1 in 10,000, were deflected, and they were deflected much more sharply than would have been expected for a tiny corpuscle. The alpha particles had to have been hitting something much bigger and more dense than a corpuscle, since those corpuscles/electrons were not that big. Since it couldn't have been the electrons that the alpha particles were hitting and being deflected from, Rutherford proposed that the alpha particles were instead hitting the positively charged area, which was compact and located in the center of the atom in a region we now call the nucleus. And here I've drawn out a model of Rutherford's atom, which has the nucleus in the center and the electrons floating around on the outside. Based on the frequency of the alpha particle deflection, 1 out of every 10 to 20,000 alpha particles were deflected at that steep angle that hit the rim of the concave plate. Rutherford concluded that the diameter of the atom as a whole must be 10,000 times bigger than the dense, positively charged nucleus. This revolutionized our view of the atom, which became complete in the 1930s when the neutron, which was a neutral or zero-charged particle, was discovered. So we're putting a neutron right there. Thus, our final conclusion is that the atom is composed of protons, neutrons, and electrons, with the protons and neutrons, which are larger and approximately the same size, hanging out in the center and the nucleus, with the negatively charged electrons, which are equal and opposite in magnitude to the protons, but much smaller, on the outside.